If you love fuzz, you love germanium. Germanium's a key component in many pedals, and it's a type of transistor not manufactured anymore, so most of them are what you call new old stock, so you have to get them from, I don't know what to call them, boutique suppliers off eBay, or there's quite a few in the US that test them for you in advance, but we're going to do that testing in this video. So my Konkorski is based on a Fuzz Face. Both of those use the specific germanium topology, the gain circuit, and the choice of germanium for these kind of circuits is very important. If you get it wrong, you're going to get the wrong type of gain, or you're not going to get enough gain. So we're going to measure gain. Before we go on, I just put out my new Primal Screamadelia pedal, because that album was very important to me back in the day, and I just received my new 30th anniversary pedal, and I just wanted to show it because of the influence Primal Scream had on me back in the 90s. So on to do some measurements. One way to measure the gain of a germanium transistor is to use a component tester. A lot of people use a peak atlas. I just use this one, but then again, I've got a curve tracer that I can do more detailed measurements with. So I simply press this button and it starts the measurement, and it's going to tell me a few things. One that's quite important to me is to understand which pin is which. This is a Soviet MP28, and so there's not a lot of documentation. So knowing which pin is which is actually quite a good feature. And then it shows me the gain, or the HFE. Let's run it again. It shows me the gain, or the HFE, of about 76. So it's pretty low gain for a fuzz. And also notice that it's small h, capital F, capital E, which means that is the DC gain. So this doesn't show me the AC gain of the transistor as well. So I'm going to perform both measurements on the curve tracer and see if there's a difference and how and what that difference would look like. This is my curve tracer. It's a Tektronix Type 575. I acquired it from one of the universities here in the Bay Area a few years ago. It's quite a terrifying instrument. It has a lot of controls. But if you imagine, it's essentially a BJT circuit, bipolar junction transistor circuit. So you've got a resistor on the base, and you've got a resistor on the current, and you can on the collector, and you can adjust those resistors, and you can apply different rail voltages. Those are essentially what the controls are going to do. Because the gain calculation is essentially the ratio of the current going into the base versus the current going through the collector. So the current going through the collector is going to be a lot larger, and that's our gain, and that's what we're going to measure. One of the nice features of the curve tracer, it allows you to test two transistors, and you just flick this switch between them. If you want to find what we call a matched pair, if you're doing like a Darlington gain stage and you want to use the gain amplification, this is a great way to flick between two transistors and determine the gain or the matching between them. Also, if you want to do something on the output stage as well. And there's two types of connector, like a Hall connector here, and then you've got these banana plug connectors here if you're using larger transistors, or you just want to put your transistor on the end of the wire, and then you just flick the switch from here back to here. And also there's a center position, so you can just switch the trace off. So we've got it on this transistor. And then when we look at the controls, we've got the limiting resistor here. So this is the voltage, rail voltage, and I've got it set to about 9 volts. And we're going to look what that looks like in the screen. And then this is the series resistor, or the resistor that feeds the base of the transistor. And then this is what we call a step selector, and this one is very important in the calculation of the gain and provides us with the steps. So let's look at what steps are. We have 1, 2, 3, 4, 5 steps representing the base current. Then on the on the collector, which is this vertical axis here, we count the graticles, or these solid red lines that run across the green, and we're looking for where the red line intersects, or a close place where a red line intersects a green line. So we have 1, 2, 3, 4, 5, 6, 7, 8 red lines till we get to a good intersection, and that current is set to 0.1 milliamps. So now let's do the math. So it's 8 times 0.1, and it's 1, 2, 3, 4, 5 times 0.002. Doing the math, we can see that IB equals 0.01 milliamps and IC equals 0.8 milliamps. So we divide those two and we get the HFE, the DC gain, which is 80. So let's press this, see what happens here. And 79, good enough. So we have some correlation on DC gain. So now let's take a look at AC gain. I've left the settings on the instrument exactly the same. So let's just count. So we want to calculate a delta. So we want a minimum collector current and a maximum collector current. So this is our vertical scale here that represents IC. And then each one of these steps represents IB. So for IC min, and we're looking for places where the red and the green intersect because it makes an easy measurement. So I can see there's an intersection about, say, here. Okay, so that is 2 steps and 3 graticules. So we've got 2 steps for our IB, and we've got 1, 2, 3 graticules. So that gives us our IC and IB min. Let's do the next one. So we're going to choose this one, I think. So that's going to be 1, 2, 3, 4, 5 steps of IB. It's a half. It looks like a half. It's going. So we're going to say that is 1, 2, 3, 4, 5, 6, 7, 7.5. So let's go back to the bench and calculate what values are and see what our AC gain is going to be. We left the scales exactly the same, so we were using 0.002 for the base and we were using 0.1 for the collector, and then we multiplied them by where the intersections were on the trace of the curve tracer. And so we end up with 0.75 minus 0.3 over 0.01 minus 0.004, which equals this, and our AC gain is 75. So it's lower. So under AC conditions, the gain of this amplifier is a little lower. I'd like to get your opinion if you've ever experienced any of this. Put it in the comments, and how AC gain differs from DC gain. I'm sure we could all benefit from understanding this. Now we're going to do one final experiment today, and we're going to put the transistor back in the curve tracer, and we're going to apply some heat. We can see the characteristics of these germanium transistors are running away. I have some aerosol PCB cleaner, which is cold, so let me spray that on it. So now we're getting back and we can see the 0 line again. So these things are very susceptible to heat. So I like to measure all of my germanium transistors, not only for AC and DC gain, just to know where I am, but also I do a little bit of heat analysis to determine what kind of temperature the pedal I'm using them in could withstand. I do 2 types of pedal. One that I call the outdoor all-weather, which is usually transistor based, which is usually silicon based, which is much more robust. And then for in-home use or in studio use where the temperature is constant, then I use germanium, and that's where you can really craft a gorgeous fuzz tone for the studio and what a piece of music you're trying to craft. If you want me to make a pedal for you, I can provide the curves from the curve tracer, AC and DC gain, a full analysis of each transistor that's used in, and a temperature analysis, so you know what kind of window the fuzz will work in before it breaks down. Too cold is also as bad as too hot in some cases. Thanks for watching. Make any comments down below if I've missed out anything, and looking forward to the next video.